So continuing with our notes and everything from Friday, rotational equilibrium, we talked about what translational motion was, rotational motion. And we talked quite a bit about center of gravity, also called center of mass, and how that kind of will cause objects to either be a little bit more stable or kind of topple once they go outside their base of support. So in the video that we kind of watched that went along with this, again, it was an older video, but it did a good job of walking through everything. I mentioned here. So if you have a tire iron, all right, we're going to talk about it a little bit today. But if you had the tire iron, excuse you, come on. All right, by adding an extra either PVC pipe or a different kind of extension to it, what we're doing is we're increasing the length of the lever arm. So if you try to like turn the tire iron and get the nut to turn itself, the bolt to turn, and it doesn't, and you can't use any more force, you have to then extend the lever arm to gain more leverage and therefore provide more torque getting the thing to rotate and turn. So we're going to talk a little bit about that today. Bathroom, go. So on the back part of this, we then talked a little bit about rotational inertia. So rotational inertia. All right, from your notes, guys. All right, these are parts of it in your notes. So it's the property of matter. Again, what inertia is itself, all right, is a property that resists changes in motion. So rotational inertia is a property that resists changes in rotational motion. This depends on the speed of rotation, axis of rotation, and the symbol can be used as capital I. We're not going to be doing any math of it. Yep. Now, in the video, the guy therefore then takes a tire, and then he takes the tire and starts to spin it. Now, the idea was when you're learning how to ride a bike, it's kind of difficult right in the beginning. So what he does is he takes this tire right here like I have, and he starts to give it some speed. So when you're learning how to ride a bike, it was like when it wasn't really moving, it was not super easy to stay straight up. You kind of like have a tendency to topple over. So like, why do your parents give you a push? When you give this enough speed and you grab it onto both sides and you start to turn it, you can actually feel resistance to changes of motion. Like this wheel kind of wants to stay in this, all right, frame of reference. It doesn't, in this orientation, it doesn't want to like tilt over. Like this is actual decent amount of force here. You don't believe me? Anybody wants to feel that real quick? You can. You can come up here and give it a shot. Anyone. Anybody wants to feel it. Like you can actually legit feel that. Get over here. Come on. Just grab both of the pegs and just kind of like give it like a slight tilt one way. And you can feel, right? Does it? It resists. Like, so now if you slow it down, press it up against your shirt a little bit. Okay, now give it just a tiny spin, and now do the same thing. Is there much going on? No, right? Like you can easily turn that. You can easily change that thing's motion. Now, once it was getting up to speed, though, right? Once we get it up to a certain amount of speed, how do I show my screen? And my screen only. I don't know. Can I do that? No, I don't want to do that. I want to maximize myself. I'm not sure how to do that. Here, B, here. Well, the idea was you get this thing up to a certain amount of speed, try and turn it. You can feel a resistance, right, to changing its motion. It wants to stay in this orientation, it wants to stay straight up. Now, you give it enough speed, and then just hold it with a string, All right, it's still kind of doing its thing where it's trying to basically stay, for the most part, pretty straight up. All right, now if we took away a lot of this, all right, speed from here, now it wants to just kind of be chilling. All right, wants to kind of be chilling. So once we slow it down, we take away, all right, a lot of stuff. We take away a lot of that stuff. Okay. Now, going back to notes, all right, that's kind of what he's talking about here, showing in the same concept, same idea. As he goes to like kind of tilt it one way or the other, you can actually feel there's some kind of resistance. So, what does rotational inertia depend on? Okay, well, speed is definitely going to wind up causing there to be, all right, it's harder to change something, right? So thinking about what inertia was, harder to change motion. And once we get it up to speed, it's going to be harder to change this motion than if it were kind of just chilling. Now, the other things that it's going to wind up depending on are the object's mass and how far that mass is from the center. So in this little experiment they do in this video, they have a ruler that's taped to a test tube on top of a metal rod, and we have a little pulley action here. We have a weight that's going to pull this thing down to one side. So basically, they're going to set the weight a certain distance from the top here. They're going to say ready, set, go, and they're going to time to see how long it takes to hit the bottom. So we do that. We're not worrying about numbers right now. All right, they tell you what the numbers are, like 6.7 seconds for it to go from like here to the floor. All right, but look at just how fast this rotates in comparison. All right, so watch. Come on. 3, 2, 1, let go. And right now. Okay, you see how quick that falls and the rope here unwinds? Boom. Okay, then they do it again, but now they put the two masses at the very ends here. All right, and then this one took about 8.1 seconds. So rotational inertia depends on two things. It depends on the object's mass, but then it also depends on how that mass is distributed, right? Is it close to our center of rotation or is it farther away? You guys ever see like figure skating competitions? Yeah, you know what I'm talking about? Where like they'll do like just like the spins and whatnot, and how they go in and get super tight. All right, they move everything close to their body, and they get super tight, and they get spin super fast. And then to slow down, they kind of like stick their arms out and stick like one leg out. All right, and it kind of slows them down. They didn't change their mass. All right, all they were doing is basically changing how far away it was from their center. So like they may start out with like arms wide and a foot wide, and then bring it in super close and start to spin. Now, obviously, we don't have ice. All right, ice skates, because if you did, you'd see that I'd fall immediately. I'm not an ice skater. In this, he basically has two potatoes that he stuck onto a meter stick. Okay, and he kind of rotates it back and forth, and then he takes a second one where the potatoes are much closer towards the center where his hands are, and then rotates it again. It's much easier to do. So then he's tightrope walking. He explains that on a tightrope walk, like the people that walk on tightropes, if they do it with like a bar, like a long metal bar, the reason why they do that is to distribute mass farther away from their feet. They're going to be their center of rotation, their axis of rotation. So it's going to be easier for them to basically remain straight up. It's going to be harder for them to start to turn and rotate. So the figure skater thing, all right, I don't have any weights right now, but this was like the idea. Okay, they get the girl to start spinning, moves at a certain speed. All right, the mass doesn't change. Now what she does is just change how the mass is brought in. Now, starts to spin a little bit quicker. Slow it down. Spin quicker. So when the mass is closer towards the center of rotation, you're going to wind up getting all right, pretty much a greater speed here. So then they have a question. All right, you have two spheres, all right, two discs that are same mass. One is hollow, a hollow metal ring, and this one is like a wooden block. Put them on the scale of the same mass. Which one do you think would hit the ground first? We kind of did this one last week. So what was it again?
The wooden block.
The wooden block. But they're the same mass, right? And if you feel them, you can feel the mass of like the ring. It seems like it's heavier just because it's all on the outside. But they're actually the same mass. So the reason why the wooden one, because more mass overall is concentrated towards the center. So it's going to wind up allowing it to rotate faster. And therefore, all right, produce a little bit greater speed down there and wind up winning the race. Yep. Working? No? What? There it is. Boom. All right. And then what else did we see or talk about? Okay, then we get into torque. Oh, sorry, for the notes. For the notes. So, rotational inertia depended on mass and distribution of mass. The greater the distance, all right, from the axis of rotation, whatever the mass is, the greater the distance from its point of rotation, the greater the rotational inertia, which means that the harder it is to accelerate. And then the girl that was bringing her arms close to her body to decrease her rotational inertia and wound up making her spin faster. When a solid disc and a hollow ring of the same mass rolled down a ramp, which one hit the bottom first? The solid and explain. Well, the smaller the rotational inertia, the larger the acceleration. So when a mass, more of the mass, is concentrated to the outside of the object, that gives you a larger rotational inertia, which gives you a slower acceleration. So like we had everything, you should have basically everything from here, the red line, up right now. And then we're going to start to talk about torque. All right, so write that down real quick. So then we started to talk about force. Then we started to talk about force that causes, more specifically, rotation. Now, torque is a force that is applied with leverage, and it's going to change an object's rotational motion, get it to start to move, turn, spin. So the equation that we use for torque, all right, the basic versions here, is the perpendicular force, all right, which is F perpendicular symbol. So it would look like, okay, F perpendicular times the lever arm. All right, which is letter R. Lever arm, R, is the distance from our perpendicular force to point P, which is what we are going to use. Okay, point P, which is what we call our pivot point. And we're going to represent the pivot point by a center or a small black dot or just a small dot on our bar. So now we're not going to be doing anything at angles. All right, otherwise it would have to be perpendicular, the sign of the perpendicular force times lever arm. Everything we're going to be using is perpendicular already. And so again, lever arm is the distance from the force, all right, or from the pivot point to the force, from the pivot point to the force. So out of these two, if these are identical forces, like the example of that tire iron, all right, you've put as much force as you possibly can in to try and get the thing to turn. Well, it wasn't turning. right? Why? Because we weren't able to produce a large enough torque. I've put in all the force that I possibly can, and the distance of the rod itself was only X distance. So if we wound up throwing on that extra thing of PVC pipe, okay, to extend our pivot point, and use that same amount of force, now we're able to provide a much larger torque, and that's going to or should help you, get your tires off. So if you ever need to change a tire by yourself, okay, maybe having just a random PVC pipe in the car could be beneficial. And or if you ever are working on your car or trying to replace your brakes, brake pads, or something like that, it's just a kind of a good thing to have. Okay, and so again, out of these two identical forces, who's going to produce more torque? All right, part one here or two, it would be two. All right, and the reason why is just because it has a longer lever arm, letter R. So now we're going to move on to actually solving some problems with torque. Now the video talks about, okay, and explains a couple different things. All right, how to determine the direction of our torques and how to calculate for them, how to calculate for net torque, and how to find a missing variable if it is in rotational equilibrium. All right, again, we said that if an object's center of gravity goes past its base of support, this thing will topple over. So if we had this thing kind of tilted a little bit more, a little bit more upright, so this straight line arrow was just on the inside of this corner and let it go, it would fall back down, to its upright position. Now, to determine the torque, you can know what the weight of this object is. That would be your perpendicular force times this distance, okay, from our pivot point to our force, and we can calculate torque like that. They talked about a pregnant lady, the backache, okay. What can they do to shift their center of gravity instead of them leaning back and causing low back problems? So someone said, like, oh, well, you can increase the base of support, put on clown shoes. Okay, well, that's not practical. So you guys, I see probably like 20 in here right now. What else could she do? There's about 20 of them in here. Backpacks. By putting on a backpack and loading that up, what that would do or should do, is right here. Okay, shift the center of gravity a little bit backwards so that it is now, her center of gravity, center of mass are over her base of support. So this asks, you're applying the same force on the object here. You're applying the same force, and even if there was so the same force, but the second one, they have a longer lever arm, you're going to be able to provide more torque. In this scenario, if you apply the same force, but this one is applied at an angle, which one provides a greater torque? Not the angle. It's the other one. It's this one. So if it's at an angle, you have to take sine of the angle times that number, because we only are concerned with the perpendicular spot, the perpendicular amount of force. So that would make 90 degrees, with our bar or whatever that we're using. So you can see that it kind of breaks down into these two different components. And then this force perpendicular is going to wind up being less than this guy, so it will provide less torque overall. So in a problem, how do we determine what kind of direction? There are only two directions for our torques. There are clockwise, which we label CW, and counterclockwise, which we label CCW. So how do you determine which is which? The best thing you can possibly do is determine or look at it like it were hands on a clock. So if the clock hand, if the pivot point is at the dead center, and the hand goes out to the right towards 3 o'clock, we're only going to be dealing with 12, 3, 6, and 9. Okay? Those are the only ones that we'll use. So in those cases, the down arrow or up arrow, that you're going to see, we need to be able to determine whether or not it is clockwise or counterclockwise. So I have up on the board and on your notes, right? When you find the pivot point P, look how the line extends and think of them like hands on a clock. Then look at the forces. If they would make the line, right, or the hand of the clock rotate the way that they should on a clock, that is clockwise, right? The way that time actually moves. If time doesn't move that way, it would be counterclockwise. So if we're looking at this, and we have our click, click. Okay, so if you have a bar that extends out to 3 o'clock, and you have two forces, one of them going downward, like such. Okay, that's not a very good. This is a little too tight here. So pushing this down would take this clock hand and make it go from 3 o'clock to 4, 5, 6. Is that the way that time actually moves? Yes. So that is why this dude is a clockwise force. The force on this side, if it were going upward, then they would be trying to push the 3 o'clock hand to 2, to 1, to 12. Time does not move that way, so we would say it is counterclockwise. What if you had this right here? Okay, here's my pivot point. If this is P, your pivot point, and I had a force down like this, a force up, a force down, and also a force up. Okay, so looking at the clock over here, we want to label and determine whether or not these dudes are clockwise or counterclockwise. So here's my pivot point P. That would be like we're looking at this part of the clock. Guys, this is going to be a very, very big part of this, because if you can't do this, you can't do the rest of the problem. All right, so please focus. All right. So find the pivot point. That's basically like the center point of the clock. So the left side would be like it's extending out towards the 9 o'clock. Okay, this hand would push 9 o'clock to go where? Either towards 10 or 8 o'clock. This down arrow. It would push it towards going to 8, right? 8, 7, 6. So that is not the way time moves. So that would be a CCW. Again, this force here, if we're looking at our pivot point and it extends out to the left, like towards 9 o'clock, you have an up arrow. That would be like pushing the 9 o'clock up towards 10, 11, 12. That is the correct way time moves. So this would be labeled CW. So you guys should probably maybe want to draw this in right to the top of your paper, right? Just kind of in this little space like I have. If the pivot point is here and we extend out now towards 3 o'clock, this down arrow would be pushing the 3 o'clock down towards 4 o'clock, 5 o'clock, 6 o'clock. That is the correct way that time moves. So this is clockwise. And this vector arrow here, this force, if it were pushing up, that would be trying to move the 3 o'clock hand from 3 to 2 to 1 to 12, which is not the right way. So that would be a CCW. All right, so torque directions are clockwise CW or counterclockwise CCW. This right here, if this was our pivot point, it extends to 3 o'clock, pushing it down to 4 to 5. Yep, that's clockwise. Here, this would be like going towards the 6 o'clock. So if we had our hand going down, this vector going to the left would push, right? If it's looking at the 6 o'clock and this one's going to the right, that would be trying to move the 6 o'clock to 5, 4, 3, which is not the correct way that time moves. So this one would be a CCW. Okay, does everyone have those values and everything written down? Heck yeah. Let's do it. All right, so what we're going to do, in order to calculate net torque on an object, all right, you need to know a couple things. One, if a force is on the pivot point, then the torque produced is 0, and you can cross it out. So in the video, they show this exact problem, but there is no pivot point located. So they're like, you guys can place it wherever. So if that is the case, so in the video, they're looking at this thing right here. Nope. All right, so they're saying you can arbitrarily place a pivot point wherever. Now, as long as you place it on a known distance and not somewhere like here where you're not 100% sure what everything else is, all right, if you place it on one of these known distances, all right, the problem is going to work out fine. So for the very first one, they're like, all right, if a force is on the pivot point, then the torque produced is 0, and we can cross it out. So I'm going to place this all the way at this end right here. So you guys are going to place your pivot point right here. You're going to place your pivot point right there. Now, since the 8 Newton force is on our pivot point, why would we cross it out? Well, because there's no lever arm, right? Because there's no lever arm, there's no distance from the pivot point to that force. So that is why you can cross out this 8 Newton piece. Cool, that eliminates it. The next step you want to do is determine, all right, what direction your forces are. Are they clockwise or counterclockwise? So what direction on a clock is this thing spinning out to? Okay, so if this is a clock, you got 12, 3, 6, 9. Okay, your pivot point is here, center. It goes out towards, yes, the 3 o'clock mark. So if I had an up arrow, what is that going to tell me? Is that the correct way that time moves?
No.
No, right? Because that would be saying, okay, we're going to go from 3 o'clock to 2 to 1 to 12. That is not correct. So my up arrow dudes are CCW. They are counterclockwise. And then my down arrow here would push it from 3 o'clock to 4 to 5 to 6, which is the correct way. So this 5 Newton here is clockwise. It's okay.
Is it because of you're just going based off on that one?
We're based off, these directions could change depending upon where the pivot point is placed. But because it was placed out here, right, and we extended these things, right, like out to the right like you would for 3 o'clock. You're cool with that part? So then it basically, like, if we drew little arrows, pushing this up would cause the time to go from 3 o'clock to 2 to 1 to 12, which is the opposite way, right? So that's counterclockwise. That's why we're going to put the little CCWs on the up arrows. Down arrow is the right way the time would move, so we would say that that is a clockwise force. Now, actually, can you hold on before I want to make sure we get through this one. So what you guys got to do here is you need to use, remember that torque is equal to the perpendicular force times your lever arm. We need to figure out, let's go with our counterclockwise first. So pivot point is here. The first force that I see from my pivot point that's not crossed out is what? Everybody? 9.0 newtons, or just 9 newtons. Now, how far is the pivot point from, or I'm sorry, how far is the 9 Newton force from our pivot point?
From the pivot point?
From, I should have put a P here.
What?
2 meters, right? So this 9 Newton force is 2 meters away from P. 9 times 2? 18. Now the unit for torque we had written down is the Newton meter. Newton times meter. Who was that to? Who was that to? Okay. So now I'm going to move on to the next force, my next counterclockwise force. Do I have any more?
Yes.
I do. I have one more. I have this guy, the 4 Newton piece.
So you do 9 times 4. 4 times 7.
All right. So you said 4 times 9, 4 times 7. Okay. This is I'm glad you said both. I'm glad you said both because you may not be 100% sure because you see, right, 4 newtons and you see this little mustache, looking thing, right? The little.
I think it would be 4 times 9.
It will be 9. So remember, R is how far your force is from the pivot point, all right, or from your axis of rotation. So this 4 Newton force, a good little trick you can do is basically drag your finger, or I put it at the pivot point and slide it all the way to that force. So I'm moving it 2 meters plus an additional 7. So I've moved this a total of 9 meters. And this gives me 36 Newton meters.
So we're not timing it at 9 newtons, we're doing 9 meters. Because 7 plus 2 is 9.
Yes, so this 4 Newton force here is 2 meters plus 7 meters away. So that's why we're getting the 9 meters. Now, are there any more clockwise or counterclockwise forces here? No. So, just like when we did free body diagrams and forces, if you have 2 forces in the same direction, what do you do with them? Add or subtract? Add them together, right? So since these 2 are the same direction, we're going to add these together. 36 and 18 gives me 54 Newton meters. Okay, now we need to do our counterclockwise, our clockwise torques. So the clockwise torque here is CCW. This one is clockwise, so this one here will be 5 newtons times. What do you? All right, yeah, pick it.
I was gonna say.
All right, so let's do this.
Plus 4 plus 2. Or would you do the 3?
You're right. You're right. So if you put your finger at P to go where the 5 is, you are 2 meters plus 7 plus 4. So you are a total of 13, right? Because 2 plus 7 is 9. 9 plus 4 is 13. So you are 13 meters away. And 5 times 13 is 65 Newton meters. Okay, now we got to ask, are there any other clockwise?
No.
Nope. Okay, so bet. Ms. Lombardo, what do I do now? Well, just like you guys had to try and find net forces, right? So let's say I did this. If this was 6 newtons and this was 5 newtons, and this was 15 newtons. 2 forces in the same direction, what did you do with them? We had to add them. So what's 5 and 6?
11.
So we basically have 11 newtons to the right and 15 to the left. So if you have two forces in the opposite direction. Remember, net force, we got to come down to bring only one. So how would we do that? 15 minus 11. You're always going to take the larger magnitude number, subtract it by the smaller. So in this case, all right, 15 minus 11 would have been 4 newtons to the left, because the left side had the greater direction, or had the greater size. So here, you are going to wind up doing 65 minus 54, and this is going to give us 11 Newton meters. So the net torque is 11 Newton meters, and in what direction? Who had the greater value? Clockwise. Wow, that was a really bad. Clockwise or counterclockwise? Clockwise. Bing bong, ding ding, winner winner, chicken dinner. Yes, sir.
You don't do anything with that 3 because there's no.
Because there's nothing else. There's no arrow over here. So this now, if we redid the problem, you know what? How about we do that? Look at what you just did. Look at you. You're like, look at that. I can't believe that all just dropped. Sweet.
Look what you made him do.
Correct. Just yeah, you can just leave it for now. I appreciate it, guys. No, because no.
Did anything break?
Probably not. I'm not sure. So the question was, all right, what did we do with that? This 3 here? Nothing happened because there was no force, right? Well, correct. So that 3 is there. It's not going to really give us any information, but what if we place the pivot point there instead? So this is the same same numbers, everything's the same distances. But now our pivot point is here. Our pivot point is all the way outside in this direction. So same premise as before. If we had our clock, what hand on a clock is this?
If it's going down in the opposite direction, it's counterclockwise, right?
Hold on, let me do this. Let me redo that. Click on this. Let's get our new clock. All right. We have 12, 6, 3, 9, and our pivot point. So our pivot point is over here, letter P. What direction is the bar going? Is it going towards 9 o'clock, 3 o'clock, 6, or 12?
9 o'clock.
It's going towards 9 o'clock. So we're going out in this direction. So then if you drew right, we had little arrows. One that goes up and one that goes down. One that goes up and one that goes down. The up arrow is going to push the time from 9 o'clock to 10 to 11 to 12. That means this is, nope, clockwise. The down hand, or the down arrow, would push the time hand, right, from 9 o'clock to 8 to 7 to 6. That's not the right way time moves. So the down arrow in this case would be correct, counterclockwise. So we're going to label all of our pieces. Okay, the down arrows are our counterclockwise. So I'm going to label right above them, CCW, CCW, CW, and CW. So please make sure that you guys are doing that right now. Heads up, please. So that is your first steps. You have to do that. Okay, we're looking for net torque. So we need to just figure out, all right, our total clockwise torques and our total counterclockwise torques. All right. So I'm going to do the counterclockwise first, because this is the first thing I see as I come or get off the pivot point. So 5 newtons How far is the 5 Newton force?
3.
Very good. It is 3 meters.
Which is 15 Nm.
15 Newton meters. Good. Okay. Now, you can do this. It doesn't matter how you do this, but whatever you do, you definitely need to make sure that everybody is in the correct column. Because this is one of the bigger mistakes is that people will go, okay, CCW, they got 5 and 3, they're good with that, and then they just see the next one and they're like, okay, CCW. They do, the 4 newtons and 7, and they're like, okay, this is good. So maybe I'd recommend, all right, doing all of one direction first. So if we're started with counterclockwise, I would make sure I do all the counterclockwise first. So I've done this one. I would put a little check next to it to make sure I've accounted for it. The next CCW is 8 newtons. And how far is that guy away? Well, correct, right? Because 3 plus 4 is 7. 7 and 7 is 14. 14 plus 2 is 16. So you are at 16 meters away. And multiplying that out, you should get 128 Newton meters. Okay, so I've accounted for that one. Are there any more counterclockwise forces or torques being produced? No. All right, bet. So what do I do next? Now I can go to the clockwise. First clockwise force, all right, or torque here that we're going to see is 4 newtons. And how far is this 4 newton piece from P? Well, if 4 newtons is here, you're 3 plus 4, which is a total of 4 times 7, or 28 Newton meters. And then the next force, clockwise, your next clockwise torque, I'm going to put a little check mark next to it because I know that's counted for, is the 9 Newton thing. And that 9 Newton guy is 3 plus 4, which is 7. And 7 plus another 7 gives me a total of 14. So I am 9 newtons at 14 meters away. And this comes out to be 126 Newton meters. Are all my torques accounted for? 1, 2, 3, and 4. Correct. So there's no more of each.
Now you have to add them.
Yep, so now if we just put a little separation here,
So that,
you're going to add each of them together. Because just like when we used to do our forces, right, 2 vectors in the same direction, you'd add them. So 5 and 6 would have been 11. 28 plus 15, if we add them, this should come out to be 143 Newton meters. And on this side, if we add them, this should come out to be 154. All right, am I done?
no.
Remember, why? Because they're asking me for net torque. Just like net force, there can only be one. So, in the notes, I always say, subtract the larger, all right, by the smaller. So who's the larger number, 154 or 143? 154 minus 143, and what does that give me? 11 Newton meters. And in which direction? Who had the larger direction, clockwise or counterclockwise?
Counterclockwise. I mean counterclockwise.
Clockwise, yes. So 11 Newton meters clockwise. Now, Morgan, you see that?
Yeah. I don't see this. It's just easy.
Look at this. We had 11 Newton meters clockwise, and here, 11 Newton meters clockwise. Why is that? Because they're the same, essentially they are the same drawing. We just switched a pivot point to a certain spot. So if you put the pivot point right here and redid the problem, you should come up with the same value. Or if you put it here, okay, and completed it and did the same problem, or if you put it here, all right, they would all should come out to give us exactly 11 Newton meters, all right, clockwise. Yes.
I mean, if you put it where the 4 is, would you do like the same thing with both sides?
Yes. So you would do the same thing then with a clock. All right. So the question was if you put the pivot point here. All right. So if that were the case, this side is like your 3 o'clock. So the down arrow would be clockwise. This, because it's on the pivot point, we don't pay attention to it. And then the left side is like going out towards 9 o'clock. And then this 9 o'clock vector would be clockwise. And this 8 Newton dude would be pushing it downward, which would be counterclockwise. So like a couple of those little things would need to make sure you're cleared up on. But yeah, that would be the same exact principle. All right, flip it over. All right, when an object is in rotational equilibrium, so think about 2 kids on a seesaw. All right, if you have 2 different sized people, can you play on a seesaw?
Yes, just somebody else doing more of the work.
Someone else, right? Now, if you were trying to get the seesaw to balance out and be like straight, could you do it?
No.
If they're 2 different sizes?
I mean, if they're the same size, yes.
If they're the same size, yeah. But what if, all right, you have like a younger sister, all right, and she's sitting on this end, and she's only 500 newtons, and you're 700 newtons, and you're 700 newtons. So would you be the same distance away, or would you need to be farther or closer? You would need to be closer. Why? Well, if you're a larger force, let's say just 700 newtons, you would need to be closer because, remember, torques are the force times lever arm. So if I multiply the larger weight by a smaller lever arm, I can get the same amount of torque as a lighter object with a longer lever arm. So when an object is in rotational equilibrium, okay, it can be at rest or rotating uniformly, which means like constantly. All right, so it's not accelerating crazily. Okay, so therefore the net torque on these objects has to be 0, which means the clockwise and counterclockwise torques have to be equal to each other. So if that is the case, remember that torques are perpendicular forces times lever arms. Perpendicular forces times lever arms. So we're going to only do this for one example, or for these examples where we have to basically have something in rotational equilibrium. You're only going to wind up with 2. So it says a seesaw. This seesaw is 3.2 meters long. So from one end to the other. That's not as centered as I wanted it to be. Damn. That's better. And it says the pivot point is at the center. So, boom. A girl weighs 580 newtons, sits at one end. So I'm going to put the girl arbitrarily on the left end. All right, she is 580 newtons. And now, do you guys agree, right? If someone's heavier, they need to be a little bit closer if we want to get the seesaw to be flat. Do you guys agree with that? So the boy needs to be closer than the girl. We don't know that distance yet. So I'm just going to, just draw an arm, a little vector here. and be like, all right, this is the boy. He's 670 newtons. We need to try and figure out how far he needs to be from the pivot point. We need to know R. R is our question mark here. So we're literally only going to use this equation, guys. We're going to basically use this equation, right? Since the torques have to equal, if we know their weights, all right, which is going to be the force, times their lever arms. Darn. I don't know how far the girl is from the center. Well, think about it. It says she's at one end. If the whole thing is 3.2 meters,
It's half of 3.
it would be half of 3.2. So 3.2 divided by 2, 1.6. So we now know, all right, our clockwise and or counterclockwise. So who's clockwise? Well, we drew a clock out. Here's the one line. Here's a pivot point. This goes to 3. This goes to 9. This is pushing it down. That would push time from 3 to 4 to 5 to 6. So this dude is clockwise. This down arrow on the 9 would push time from 9 to 8 to 7 to 6, which is not correct. So that's counterclockwise. So our counterclockwise and clockwise torques need to be equal, which means their force times lever arms need to be equal. Hold on, we'll be finishing up in 1 second. All right, so the girl is the counterclockwise, so we know that she is 580 with a lever arm of 1.6, and the boy is 670 R. Multiply this side together. You're going to get 928. So yep, is equal to 670 R. If you divide both sides by 670, you are going to wind up getting a value of. So we had to use this equation here. All right, force times lever arm has got to equal this force times this lever arm. So by setting them equal to each other, you have 580 times 1.6 is going to wind up equaling 670 R. Multiply these out, you're going to get 928 is equal to 670 R. Divide both sides by 670, and then you should be left with an R value of 1.385 meters. All right.